Hi, so in this video, we're going to finish our constructions of measure by introducing proposition 1.14. And the proposition 1.14 is about, it's kind of like summary between the outer measure and the pre-measure, and then it also introduced the measure and sigma algebra. Okay, so let's introduce the theorem. So and then the setup should be the same as previous. So we also have an algebra. So that A is an algebra. And mu naught is what? Is a pre-measure. Okay, so we have A is algebra and the mu naught is premeasure, and M is sigma algebra. This is a new element. So notice that in 1.11, we're introducing outer measure, and in 1.13, we're introducing the premeasure and outer measure. And now what we're doing, we kind of like connect them more tightly by introducing the sigma algebra generated by the algebra A. So let me write this as this font. Otherwise, it's going to be really similar as mu. So M is the sigma algebra. Okay, so here I'm the sigma algebra, and what is our claim? Are we ready to introduce a claim? Yes. So claim 1. There exists mu, which is measure on M such that mu restricted on A is equal to mu naught. Okay. Mu is equal to, there exists a measure on M. Okay, and notice that mu star is a measure is a measure on mu star measurable sets. Okay. Let me think about this. And we showed that for every A in the algebra, A is mu star measurable. Is mu star measurable, right? Okay, we showed for all A in A is mu star measurable. Since M is the sigma algebra generated by A, that means by if you still recall proposition 1.1 or lemma 1.1, 1.1, M is a subset of mu star measurable collection. And since mu star is a measure and actually is a complete measure mu star measurable collection. Okay, since mu star is a complete measure of mu star measurable collection, and we have M is a subset of mu star measurable collection. So mu star restricted on M. Is it a measure? Is a measure. And since, so that's why we define mu to be this. Okay, since mu star restricted on A is equal to mu naught. Okay. And mu is equal to mu star restricted on M, and notice that A is a subset of M. Therefore, mu restricted on A is equal to mu naught, because the domain of mu is M, and then the domain of mu star is mu measurable collection. And we also know that so both of them include the domain sigma algebra, and then and then they are the same on M's, where M contains sigma algebra, so they are the same on A, the sigma the algebra. So therefore, mu restricted on A is equal to mu naught. So sorry, I'm trying to I'm trying to list the claim, but I guess I went a little bit farther to give you a short proof, because the proof is really short. So I don't want to spend time later on in the like official section of the proof. So so this actually gave us the existence of measure on M such that this measure is equal to M naught. And then the claim 2, so claim 2, if I have a mu is another measure. So notice that we have all the measure and we have sigma, we have algebra, and we have so it is possible that there are multiple measures. So there's no theorem saying that once you have measures, that the measure is unique on that sigma algebra. You could definitely have more than one measure on the sigma algebra. So if mu is another measure, and here, but from proposition 1.11 to 1.14, we're kind of focused on constructing a measure through a particular way, which is originated from Caratheodory theorem. But there are definitely other measures. And here we assume, okay, what if there's another measure mu that is not, for example, specifically constructed in this way? Okay, then for all E that is in M, mu E is smaller or equal than mu of mu E is smaller or equal than mu of E is smaller or equal than mu of sorry, mu of E, right? Mu of E. And then what do we have? If mu of E is finite, sorry, if mu of E is finite, then mu of E is equal to mu of E. And furthermore, if mu is sigma finite, oh sorry, if mu naught is sigma finite, then mu is unique. Unique extension of mu naught to measure on M. So let me just like rephrase let me explain. So as I said before, there might be multiple different measures on the sigma algebra M generated by the algebra A. So how to construct those measures? By using proposition 11 to proposition 14, it gives us one way to construct such measure. And now we're comparing this constraint, the measure constructed in this way with any other measure defined on M. So if the measure constructed in this way is infinite, then mu E is smaller. So let's just start over. So mu E is smaller equal than mu E is smaller equal than mu E. But when mu E is finite, then mu E is equal to mu E. That means if the measure of E is finite, then mu E is equal to mu E. So for example, if your whole universal space has finite measure, for example, mu X is equal to is finite, then for every subset E, in particular, for any element in the sigma algebra, mu of that set is going to be finite. Therefore, your measure is unique. But But if you it is totally possible that the measure of your universal space is infinite. So in that case, we can only like guarantee that mu e is smaller or equal than mu e. And then another thing is that when you look at your mu naught with the premeasure, if the premeasure is sigma finite, which means that if you have a set that has infinite premeasure, then that we can write that set there exists a disjoint, a collection of disjoint sets such that the union of that set is equal to the set with infinite premeasure. And then if that happens, then your construction mu is a unique extension of mu naught on M. So I'm not saying that mu is unique on M. I'm saying it is true. So mu, there could still be a multiple different measure mu on M, but for example, mu1 and mu, right? And mu is an extension of mu, and mu1 is not equal to mu. Yeah, mu is an extension of mu naught, and mu1 is different from mu. Then what we have is that what we know if we're given that mu naught is sigma finite, we know that mu1 is definitely for every e. So there exists e in the algebra A, mu1 e that's not equal to mu naught e. So that means mu1 is not an extension of mu naught. Mu is the only extension, the only unique extension of mu naught, given that mu naught is sigma finite. Okay, so let's keep proving. So we have to prove 1, 2, and 3, right? So let's prove 1. If mu is another measure, then for all e in M, mu e is smaller or equal than mu e. Let's think about this. So again, it's gonna use something that we saw before. Mu of e is equal to into 1 summation 1 to infinity mu naught of aj, where aj is in A and E is a subset of union of aj. Hence, so if we pick arbitrary sequence aj such that aj is in A and then E is a subset of the union of aj, only need so show that mu of E is smaller or equal than 1, this particular, then we're done, right? Okay, so how do we show this? Mu of E is smaller or equal than mu of union of aj by monotosity of measure, and smaller or equal than summation 1 to infinity mu of aj, and because aj's are in A, so it's equal to 1 to infinity mu of aj or mu naught of aj. So we're done in this direction. Hence mu e is smaller or equal than mu of e. So remains to show that mu of e is smaller or equal than mu of e. So mu, so mu of e is equal to, so what do we want to show is, we want to show the inequality. No, we don't want to. No, because I'm sorry for confusing you. So here we only need to show this inequality. Cool, so we're done with 1. And then for 2, so given if mu of E is finite, then so I'm gonna highlight the trick here. So because of this infinite relationship, then pick arbitrary is enough to just pick an arbitrary and show that this is more equal than this for any arbitrary. Okay. Okay, so if mu E is less than infinity, then mu of E is equal to mu of Y. Well, again, it's a trick that you have seen before. If mu of E is less than infinity, and we call the definition mu of E is equal to infinite summation mu naught of AJ. AJ is in A and E, the subset of the union of AJ, right? Okay, so so for any epsilon, there exists sequence AJ such that mu of E, no, such that we have this. Okay. Okay. Okay, we have this, and then we can let's think about this. Mu naught union AJ by subadditive premeasure. Okay. And this is equal to mu union of AJ. And then let's just define that union of AJ to be A. Okay, so we have mu of A sine minus E is less or equal than epsilon, where A is the union of AJ, and it contains E. So this actually have the idea that once you know that your set has finite measure, then you can exhaust your collection. Okay, and then recall our goal is to show that. So we already showed that this is always hold, right? So this always hold. So we just need to show mu e is smaller or equal than mu of e. So mu of e is equal to mu of e, or mu of e of, let me think, 1 second, a side minus e. Okay, so mu of e is smaller than mu of a because monotonic measure, which is equal to mu of e plus mu of a side minus e, and mu and mu, but e is a set on m, and a side minus e. Oh, I'm sorry. A. How do I know that A is in premeasure? How do I know that A is in algebra? So A, what is A? A is a collection such that E, oh, okay, so we know that AJ is in A. But do we know that A is in algebra A? I don't think A is in algebra A because we're not given that the infinite union is in A. We know that A must be in M, but mu and mu, they're not equal on M. Mu and mu, they're equal on A, the algebra, because they're both the extension of mu naught. Let me see about this. Okay, so we need to prove a lemma before we continue. Okay. Mu of A is equal to mu of AJ. And this, you can definitely make it as increasing sequence. So it's equal to the limit of n goes to infinity b of AJ. We change this to J. And this is equal to the limit J is for infinity mu of AJ, because mu and mu are same on the algebra A. And by the continuity on below, again, we have mu of limit of AJ 1 to infinity. This actually tells us that if you know that your measures are the same on the algebra, if you know that your measure is the same on the algebra, and you have a countable collection of sets in your algebra, and they're disjoint. No. If you have a countable collection of sets in your algebra, and you know two measures are extension of that, then those two measures on the union, they are the same, even though the infinite union may not be inside of the algebra. So here the deal. So I want to show that mu A is equal to mu of A, but A is not in the, but A is actually not in the sigma algebra. So we cannot say that. The only thing we know is that mu A and mu A are same on algebra. So but we also know that each component of this kind of a collection of sets is in algebra. Therefore, we can use continuity below to argue that once you have a collection of sets in your algebra, then the union, and you also know that two measures, they are the same, they are extension of the premeasure mu naught on the algebra. Then no matter whether or not the infinite series, infinite union is in algebra or not, the measure of this infinite union is equal to the measure of the other measure on this infinite union. So if we have that, then we have mu a is equal to mu a then. And what is mu a? Mu a is equal to mu of union of aj. So what do we want eventually? We want mu e, right? What is what are we proving here? What are we proving here? It's finite. Okay. So those are disjoint. So this is equal to a side minus e plus mu of e. And right, this is smaller than epsilon plus mu of e. And let epsilon goes to 0, then we have mu of e smaller or equal than mu of e smaller or equal than mu of e. Hence we have mu of e is equal to mu of e. And we prove the second one. Of course, I think this lemma is very hard to think about, this lemma, and then corresponding to this part of the proof. And write it in this way. And because A contains E, and eventually you want to have mu of E inside, so it's kind of natural to split your A into A side minus E and E, and then use this inequality. Okay. And then what is third one? So suppose. So suppose what? Suppose that mu of E let's see. Suppose that suppose that mu naught is sigma finite. Then mu is unique measure on M. So let E is an element in M, then mu naught of E is equal to Then we have mu naught of E. Right, let me, there exists, okay, since we can disjointify, so, okay. Mu E is equal to, I'm thinking about why. Oh, because mu naught of AJ is finite, and mu of AJ is finite, and mu of E intersect AJ is smaller than mu of AJ is finite. And when set has finite measure, it equals mu of E intersect AJ. So this actually uses 2. So 2. And this is equal to mu of union or E intersect union of AJ, mu of E intersect X, which is equal to mu of E. And finish the proof.